Brandon Seward is going to lecture on cost L2 Betti numbers on the sofic entropy of some algebraic system.
So I'd like to thank the organizers for the opportunity to be here today. So I'll give another entropy talk this morning, and I'll be making connections between algebraic actions and cost and L2 Betti numbers. And everything I'm mentioning is joint work with Damien Gabriel. First, I'd like to recall two well-known properties of classical entropy. So if gamma is a countable amenable group, then we have two well-known properties in addition to others. One of them is monotonicity. So if gamma acting on y is a factor of gamma acting on x, then the entropy cannot increase. So the entropy of the action on y is at most the entropy of the action on x. And this is true both topologically and measure theoretically if you put a measure on x and push it forward to y. Another well-known property of classical Kolmogorov-Sinai entropy is the Javinsky addition formula. So this says that if G is a compact group and gamma acts on G by continuous group automorphisms, and N is a normal closed subgroup, which is G invariant, gamma invariant, then the entropy is additive. So the entropy of the action on G is equal to the entropy of the action on N plus the entropy of the action on the quotient G mod N. And again, this is true both topologically and measure theoretically if you use Haar measures. In the original case where gamma is the integers, this was proved by Javinsky. And there were several progressions. It was improved to Z the D and further. I don't remember the whole list of people, unfortunately, but in this general form here for an amenable group, this is due to Hanfeng Li and also due to Douglas Lind and actually I can't remember, did Lind have a collaborator on that? Does anyone remember? Klaus Schmidt. So sorry. Yeah, when I was going to say this, I realized, I forgot to look this up beforehand exactly. I'm sorry. My apologies. Okay. Okay, so in the classical setting, we have these two well-known properties. And now I'd like to share with you an example. There's an example you've maybe heard of. It's been mentioned a few times already. This example is from Ornstein and Weiss from 1987. So let F2 be generated by A and B, be the rank 2 free group, and define a map theta from Z mod 2Z to the F2 to Z mod 2Z cross Z mod 2Z to the F2 as follows. So theta of x, if you evaluate it at a group element G, well, it has two components. And so the first component is x of G minus x of GA. And the second component is x of G minus x of GB. And so theta is not too hard to check. There's a continuous gamma equivariant group homomorphism. Here, Z mod 2Z to the F2, you can view this as a compact abelian group just using coordinate-wise addition mod 2. Similarly for this group over here. And with this group structure, this map is just a continuous group homomorphism, but it's also equivariant with respect to the action of the free group. And now using the fact that the Cayley graph of the free group is a tree, it's an easy exercise to see that theta is surjective. And being surjective and being a group homomorphism, this means that it must take Haar measure to Haar measure. And here in this example, the Haar measures are just the Bernoulli measures. So here with the 1/2, 1/2 measure, and here it's 1/2, 1/2 by 1/2 by 1/2. And so this example suggests that entropy cannot be extended to actions of free groups. Which is kind of surprising and disturbing, or at least it was in 1987. And the reason it suggests this is because from the classical framework, we would expect that this Bernoulli shift to have entropy log 2, and we would expect this Bernoulli shift to have entropy log 4 if entropy were defined for a free group action. But then this would violate both of these properties. You'd be mapping from log 2 entropy to log 4 entropy. You'd be going up in entropy, and I just touched that, really. There we go. So it would violate both of these properties. So it seems to suggest entropy cannot be extended, but as we found out this morning with the previous two talks and also with Miklos's talk the other day, entropy has been extended to actions of free groups and actions of sofic groups. And so I'll be discussing two entropies in this talk. One of them is sofic entropy, which you've heard a lot about. Another one is rockland entropy, which I'll define soon. And it is true that this action does have entropy log 2, and this action has entropy log 4 for both sofic entropy and rockland entropy. And so indeed, this example does show that both of these properties fail for rockland entropy and sofic entropy. I should mention, though, that there is another notion of entropy. There's an entropy-like quantity, an isomorphism invariant, introduced by Lewis Bowen. It's called the F invariant. It's defined only for actions of free groups. And Bowen and Gutman have a paper where they show that for the F invariant, there's a large class of actions where the Javinsky addition formula does hold. It's still open if it holds in general for the F invariant. But in this talk, I would like to talk about more general groups, not necessarily free groups, so I won't be working with the F invariant. I'll be working with sofic entropy and rockland entropy, which I'll define soon. And so this new addition to entropy theory that has recently emerged with sofic entropy and rockland entropy, it's very exciting. In some ways, entropy behaves in the way classical entropy does, and then in other ways, it behaves in very surprising ways in violating these classical properties. And so it's an exciting time that we have this problem in front of us. We have a problem to try and understand factors in this new setting. What factors do to entropy for actions of non-mendable groups, and what happens with the Javinsky addition formula. And I say this is exciting because there's no parallel in the mendable world to tell us what we should expect the answers to be to these questions. And so sort of a long-term program or question I have, it's kind of vague though, is there a structure theory for factors and entropy for actions of non-mendable groups? Whatever that means, a structure theory. But right now, we mostly have a lot of questions. Right now, we know very little about the failure of these properties for non-mendable groups, and we know very little about what that means, and we have very few examples. So for this reason, Damien and I, we wanted to try to examine this Ornstein-Weiss example from a different perspective and see if we could learn something new. And so we considered the following generalization to their example. So I'm referring it to as a generalized Ornstein-Weiss map. So let gamma be a countable group. And say gamma is generated by a set S. Here S can be infinite. So it's not necessarily a finite generating set, just a generating set. And now we can define the generalized Ornstein-Weiss map with respect to S. It's we also need to choose a finite abelian group K. And now we can define the generalized Ornstein-Weiss map as a map from K to the gamma to K to the S to the gamma as follows. So evaluate dat G, evaluate at X, and then at the group element G, and then at the generator S, it has value X of G minus X of GS. So this seems like the natural generalization of the map to other groups, but now I'd like to note that it actually does not depend on the generating set S. So just note that the kernel of this map is isomorphic with K. It's in fact just the constant functions. The kernel is precisely the constant functions which we identify with K itself. And so this means that the generalized Ornstein-Weiss map is simply the quotient map from K to the gamma to K to the gamma mod K, mod the constant functions. And I would like to mention that aside from any connection with the Ornstein-Weiss example, this particular factor map has already been studied because there's this interesting phenomenon. For actions of amenable groups, it's known that factors of Bernoulli shifts are Bernoulli. So for Z, this was proved by Ornstein. And for amenable groups, I'm not certain, but I think it was in your paper with Ornstein, right? Ornstein-Weiss? Yeah. So for amenable groups, factors of Bernoulli are Bernoulli shifts, or isomorphic to Bernoulli shifts. For non-amenable groups, it's known to be false. Popa proved that for many non-amenable groups, such as property T groups, this particular quotient map, the image is not isomorphic to a Bernoulli shift when you equip it with Haar measure. And I should also mention that Tim has a new proof of this fact for certain sofic groups with property T using sofic entropy type of ideas. He has a proof that, again, this is not isomorphic to Bernoulli. And then it's also known that if gamma is a free product of amenable groups, then this is isomorphic to Bernoulli when you equip it with Haar measure. And this is something else I forgot to look up. Let's see. So there's three authors of that result. One of them is Sven Rahm. The other one's Stefan Weiss. And the third one, his last name starts with an M. Mischart. Anyone remember? No. I meant to look that up this morning, and I apologize. I forgot. Anyways, but so there's this interesting question for non-amenable groups. When is it the case that factors of Bernoulli shifts are isomorphic to Bernoulli? And these particular factors of Bernoulli are an interesting example where we have some partial results. It's not isomorphic to Bernoulli when gamma has property T. It is if it's isomorphic, if gamma is a free product of amenable groups.
Popa's result has nothing to do with entropy?
No. Popa actually proved something much stronger. He proved that for property T groups, actually a more general class of groups, but for property T groups, these factors, if you equip them with Haar measure, they're not even orbit equivalent to Bernoulli. He computed I think what he called the first cohomology group of these things, and also for the Bernoulli shifts, and he showed that they're not isomorphic, and it's an orbit equivalence invariant. So, okay. So now before stating our main theorem, there's a few definitions I have to go through, which kind of ties in with the title, so you can imagine what I have to define. The first thing is cost. So if you have an action, gamma on x mu, and this is probability, measure preserving, ergodic, and free, then the cost of the action is defined to be the infimum of 1/2 the average degree of measurable graphs G on X such that the G connected components are precisely the gamma orbits. So for an example of such a graph, you can take a generating set for your group, and then any 2 points in X, you can make an edge between them if a generator takes one point to the other. And this would give you an example of a measurable graph whose connected components are the orbits. And then you can look at the average degree, half of that, and then you have to consider more general graphs to get the cost, but that's sort of the basic idea. And now for a group gamma, the cost of gamma is defined to be the infimum of the cost of gamma actions. And the infimum is taken over free ergodic probability measure preserving actions. And there's a related notion of supremum cost, which I'll need. So the supremum cost, it's the same thing except you take the sup. All right, so next I need to define L2 Betty numbers. Oh, and actually, so the definition of L2 Betty numbers is a bit technical, and due to time I can't really define it in full generality. But I'll give you an idea of what the first L2 Betty number is. But again, I just want to give you an idea instead of the full precise definition because it's a little technical. So just to make things a little bit simpler, assume that you have an action, gamma acting on L, which is a free co-compact action. And here L is a simplicial complex. And it's simply connected. So for example, if gamma is finally presented, then you can add 2 cells to the Cayley graph of gamma, to any Cayley graph of gamma, for the relations. And then you can triangulate in an equivariant way in order to get a simplicial complex which is simply connected and where the action is co-compact and free. Okay, so the first L2 Betty number of gamma with this assumption is simply the von Neumann gamma dimension of the reduced first L2 cohomology of L. And yeah, so again, it's a technical definition, and I don't have time to go into what precisely is von Neumann dimension and the reduced cohomology, but maybe if you've seen it before, this will at least remind you what the definition is. I can say something that might help. So there's this nice result due to Russell-Lyons that says that the first L2 Betty number of gamma is equal to, let's make sure I get this right, So it's 1/2 the average degree of the free spanning forest minus 1. And what the free spanning forest is, it's the following. So you take a Cayley graph for gamma, and now you take a sequence of finite subsets that are increasing, and say they're connected with the induced subgraph. And now for each finite set, you look at the collection of spanning trees on that set, and you attach to it the uniform probability measure. And now as you have the sequence of sets, you have a sequence of probability measures on these subtrees, and you can take a weak star limit of those measures, and this is the free spanning forest. And you can take the average degree, and so it's a different way to get the first L2 Betti number. Okay, questions so far? All right, so next I need to define rockland entropy, which luckily won't take too long. So let's say you have a probability measure preserving ergodic action. So recall that a partition P is generating if the smallest G invariant sigma algebra containing P is Arbor sets up to null sets. So add in the null sets as well. And then you get Arbor sets of X. Or all measurable sets, if you prefer that term. And also recall, so we've seen this a few times, but I'll just remind you, if P is countable, a countable partition, then its Shannon entropy is the sum over the classes in your partition negative the measure of that class times log the measure of that class. Okay, now the rockland entropy is defined as follows. And this should be a gamma, my mistake. I may do that again. So the rockland entropy of the action of gamma on x mu, this is just defined to be the infimum of the Shannon entropy of partitions P, where P is a countable generating partition. So I should say a few things. First of all, if gamma is just the integers, then this is classical Kolmogorov-Sinai entropy. It's the classical entropy. And this was proved by Rockland, which is kind of the reasoning behind the naming. And it's actually true more generally for amenable groups. If gamma is amenable, then this quantity is equal to classical entropy. And so it gives you a reasonable generalization of entropy to actions of arbitrary countable groups. And I should also mention that it's always an upper bound to sofic entropy. Questions? Okay. All right, so I'll state our main theorem now. Again, this is joint with Damien Gaborio. So let gamma be a sofic group, and let sigma be a sofic approximation to gamma. So again, we got kind of sidelined with the definitions, but we're interested in this generalized Ornstein-Weiss map. We're interested in understanding what happens to the properties of monotonicity and the Javinsky addition formula. And so the Ornstein-Weiss map is this quotient, and so for that quotient, to begin with, you can do two things. First of all, you can look at it topologically and ask what its topological entropy is. And you can also look at it measure theoretically with its Haar measure. And so we show that these two are actually equal. So you can view it whichever way you prefer, measure theoretically with Haar measure or topologically. And as a lower bound, we have, I forgot to say, now K is not a finite abelian group, but a finite field. We have a lower bound by the logarithm of K times the first L2 Betty number of gamma plus 1. And on the other side, as I just mentioned, it's always true that sofic entropy is bounded above by rockland entropy. And now for an upper bound to this entropy, we obtain the supremum cost of gamma times log K. And I should mention this first inequality actually requires gamma to be finitely generated. So you need an additional assumption for the first inequality. And the last inequality is completely general. You do not need a sofic group. So this holds for all countable groups, gamma. Okay, so there's a few things I should say about this. There's sort of a lot going on and a lot hidden just underneath the surface. So the first thing that probably stands out is the two extremes here. And as you may know, there's two well-known open problems. The first is the fixed price problem, which basically asks whether or not the supremum cost is always equal to the cost. Another open problem is whether or not the cost is always equal to the first L2 Betty number plus 1. And so, of course, if both of those open problems had positive solutions, the two extremes are equal, and so we have equalities throughout. Also, I should mention Miklos talked about the Luke approximation theorem and characteristic P and connections with sofic entropy. And you see that here as well. The sofic entropy we obtain here is actually the lim sup of normalized, if the group is residually finite, let's say. The sofic entropy we obtain here is the lim sup of normalized Betty numbers computed over the finite field K, times log K, of course. And so this creates an interesting relationship between this question that Miklos was asking, whether or not the Luke approximation theorem holds in finite characteristic, meaning, do the limits converge? What does the limiting value represent? And it sort of ties in with a similar problem with sofic entropy, whether or not sofic entropy depends on the choice of sofic approximation. So these two are kind of connected. And then I should also mention that this inequality here, I said this equality holds in general, but in fact we don't know. It's an open question whether or not sofic entropy is always equal to rockland entropy when the sofic entropy is not minus infinity. That's an open question.
So you say if there are all equalities, then the question to the Miklos question is that it converges to first Betty number.
The normalized Betty numbers mod P. I believe so, but I believe you could probably deduce it more quickly if the supremum cost was equal to the first L2 Betty number plus 1. But I haven't checked, but I'd imagine there'd be a more direct implication. But this would imply it, yes. Other questions?
Some concrete example of group for which it's unknown, either it's the same or not.
For what, the...
Rockland and for sofic.
Oh, for any non-amenable sofic group, even for the free group, we don't know if they're equal or not, whether or not sofic entropy and rockland entropy are equal, aside from sofic entropy minus infinity. No, we don't even know for factors of Bernoulli. So we know for Bernoulli shifts over sofic groups, they're equal. It's kind of immediate if you understand the definitions, and if you know this fact for sofic entropy, that it gives you the expected value. Okay, so I mentioned all these open questions, but I maybe got off on a tangent. So in terms of the properties of monotonicity and Javinsky addition formula, so this is saying that positive first L2 Betty number implies that this generalized Ornstein-Weiss map violates the Javinsky addition formula, violates monotonicity. While on the other hand, if the supremum cost is 1, meaning you have fixed price 1, then the generalized Ornstein-Weiss map preserves entropy. Okay, so with the remaining time, I want to say a little bit about, there's sort of 3 statements occurring here. There's this inequality, there's this equality, and then there's this inequality. And so I'd like to say a little bit about each one, maybe give you a little bit of an idea of what goes into the proof. So for one, so as you saw this morning, you saw a lot of definitions on the formula for sofic entropy. It involves counting these finite models which approximate the action in a certain way. So the intuitive idea behind one is that in certain situations, such as the situation we have here, topological entropy is given by, in some sense, perfect models. So I'm just going to be vague about what this means. I'll show you what it means in the special case of a residually finite group. That'll be a little bit easier to understand and a little bit faster. So let gamma be residually finite. And let sigma, so sigma, it's a sofic approximation to gamma, but we want it to actually come from quotients. Yeah, so this is an approximation via finite quotients of gamma. And now let K be a finite group, not necessarily abelian, if X contained in K to the gamma is a subgroup and a subshift of finite type, then we have the following. The entropy with respect to this sigma of the action of gamma on X, this is topological entropy. This is equal to the limit supremum of log of the number of gamma n periodic points divided by the index of gamma n within gamma. And so this is, in the classical situation, this is a very typical type of thing. You show entropy is just given by exponential growth rate of periodic points. So it's sort of a nice analog of what you have in the classical case. And this roughly is what I mean by perfect models. So we prove something more general that holds for general sofic groups. But in some sense, under the right assumptions, such as the assumptions I have here, you can compute topological entropy via these like perfect models, which in this case is periodic points.
Can I ask a question?
Yes?
If you assume the action is expansive,
Mm-hmm.
do you still need finite group, or is it enough just to have expansive?
I'm not sure. I'd have to think about that. It's a good question. Okay, so next I'd like to remind you of the Luke approximation theorem. It will tie in with the idea behind the proof of 1. And so again, let's assume that gamma is residually finite, and that you have a chain of normal subgroups of finite index with trivial intersection. And suppose that gamma acts on L, and this is a free co-compact action on a simplicial complex, and L is simply connected. So the Luke approximation theorem says something more general. I'm saying just the version that we need here. Then the first L2 Betty number of gamma is equal to the limit of the dimension. You look at the first cohomology of L using, say, real coefficients. You take its dimension and you divide by the index of your, so you don't use L, you quotient out by gamma n to get a finite simplicial complex. And now you divide by the index of gamma n inside of gamma. So there's just the Luke approximation theorem.
Look at the monitor.
Did I do something wrong?
H1 of something, comma R.
Okay, all right, yeah, I'll clean that up. Yeah, so it's the dimension of the first cohomology. You take your simplicial complex L and you mod out by the action of gamma n. This gets you a finite simplicial complex. You use real coefficients and you divide by the index. Yeah. Okay. So now the idea behind 1 is to combine these two facts with the following observation. The observation is that the generalized Ornstein-Weiss map coincides with the co-boundary map. On the Cayley graph of gamma. And so now you can kind of see how 1 is obtained. The idea is that in order to compute entropy for things in this setting, we can just look at periodic points. But if you have a cochain which is periodic, then it just is identified with a cochain of this quotient. So there's a nice one-to-one correspondence. And so these two facts together sort of get you 1 with a little bit of work. And in fact, this method shows something more general. So we prove the following. We prove something more general than this, but I'll say a slightly weaker version to save time. So if gamma acting on L is a free co-compact action, and if, let's say, that L is contractible, you can get by with a weaker assumption, but again, I'm just wanting to make this simple for now. And let K be a finite field. Then the entropy, and this is for any sofic approximation sigma, any sofic group doesn't need to be residually finite. The entropy of the action on the p-1 cochains on L with coefficients in K plus the pth L2 Betty number of the action of gamma on L, which I apologize I didn't define. This is a lower bound to the entropy of the kernel of the pth coboundary map. Pth meaning going from the p-1 simplices to the p simplices, plus the entropy of the image of that coboundary map. And so what this says, it says that if you have a positive L2 Betty number, then the Javinsky addition formula fails. Right? You have the kernel, you're modding out by it, there's the image, and the entropies are not additive. You have the L2 Betty number forcing them apart. And going back, I should mention, for amenable groups, when gamma is amenable, this was obtained by gaba relic. And going back to my question I asked earlier, is there a structure theory? Will we ever really understand what happens with the Javinsky addition formula with sofic entropy? It seems suggestive, not only based on this work, but on work of other authors as well. It seems suggestive that there's maybe a strong connection with L2 type quantities. So here we showed that L2 Betty numbers are sufficient grounds to conclude that the Javinsky addition formula fails. There's prior work which is similar. So Ben Hayes proved that if you have a group with defined and non-zero L2 torsion, then it admits an action, and an algebraic action, which violates the Javinsky addition formula. And similarly, Gabor Elek showed that if you have a group with a non-zero Euler characteristic, then it also admits an action which violates the Javinsky addition formula. And I should maybe also mention that the entropy for certain algebraic actions, specifically principal algebraic actions, has been studied quite a bit in the sofic case. And there's a close connection again to L2 quantities. The entropy for principal algebraic actions, this is a result of Ben Hayes in general, that for principal algebraic actions, the entropy is given by the Fugeta-Cadison determinant, which is an L2 type quantity. And so there's the question is here sort of, with algebraic actions and the Javinsky addition formula, is it somehow always related to an L2 property, whether or not the Javinsky addition formula fails or not? It's an interesting question.
Clarify this formula. P is just any degree.
Yeah.
K, there is no dependence on K on the right-hand side?
These are the maps with coefficients in K. Yeah. Yeah, so this is mapping you from CP minus 1 LK to CP LK. Okay, so now I'd like to say a little bit about item 2 over there. And this will be pretty brief. So 2 follows from a more general result. So studying this question led us to study properties of algebraic actions in some generality. And so we proved the following. So if G is a compact, if G is a profinite group, in particular compact, but if it's a profinite group, and gamma acts on G by continuous automorphisms, and if you also assume that the homoclinic group is dense, so the homoclinic group is the set of elements G and G such that the identity group element is in the closure of the gamma orbit of G. It's like that forms a subgroup of G. If the homoclinic group is dense, then we have, and this is for any sofic group gamma, any sofic approximation, the topological sofic entropy of the action is equal to the measure theoretic entropy of the action when you use Haar measure. In particular, this theorem, with a few extra assumptions, is true for measure theoretic entropies as well. In the case gamma is amenable, it's known that you always have this equality. You don't need to assume profiniteness. You don't need to assume dense homoclinic group. If gamma is amenable, then topological entropy is always equal to measure theoretic entropy with Haar measure for algebraic actions. For sofic groups, it's open, and this is the first result giving a sufficient condition for the equality. And I'd like to say a few words about the proof just briefly. for those in the audience who have some familiarity with sofic entropy, I'd like to just say a little bit about how the proof goes. So based on what I said earlier, in certain situations, such as the situation you have here, you can compute the topological entropy by just looking at perfect models, whatever that means. You can imagine it's periodic points if you like. And these perfect models themselves form a group, a finite group. Once you fix a finite model to your group G, then you look at the models of the action. These perfect models form a group. You can equip them with Haar measure. And now it's a useful fact that if you have a surjective group homomorphism, Haar measure gets sent to Haar measure. And what this means, is that you can, to some extent, you can understand what the Haar measure is on these perfect models. You can understand it to some extent. The assumption of a dense homoclinic group allows you to do a second moment method to show that most of the topological good models are in fact good models for the measure. And that gets you one inequality, and then the variational principle gets you the other inequality. So that was fast, but yeah, just wanted to say a word about that. Are there questions? Okay, so finally.
Why is the homogenic group a group with just define it like this?
Oh, did I define it incorrectly?
They have to tend to zero or to the identity as you go out to infinity. It's not just.
Oh, you're right. Yeah. Sorry, I wrote the definition wrong. You're right. Yeah, thank you. So the definition is actually that gamma of G goes to the identity as gamma goes to infinity, meaning gamma leaves all finite subsets of big gamma.
So the closure is orbit plus identity.
Yes. Yeah.
And condition is that it's dense where? In G?
Dense in G, yes. Yeah. I should also maybe mention for amenable groups, I said this is true in general. That's due to Denninger. And his proof, I think it's 1 or 2 pages. It's not too long, but for sofic entropy, it's very unclear, at least to me, if something like this is true in general. Okay, so now I'll really briefly say something about what goes behind the proof of 3. And so first, I'd like to make 2 observations. One is that if gamma is generated by a set S, then the image of the generalized Ornstein-Weiss map is by definition contained in k to the s to the gamma. And again, so for 3, I'm going to be looking at rockland entropy. So I want to look at generating partitions for the action. So here you have a very obvious generating partition corresponding to k to the s, what your values are at the identity group element. And so this implies that the rockland entropy of this factor with Haar measure is at most cardinality of S times log of the cardinality of K. And so what we're saying is for any generating set S, the cardinality of S times log K is a bound to the rockland entropy. So you're already bounded by the number of generators to the group. We just want to show that you're bounded by this cost, which is sort of a measure theoretic notion of generating a group in some sense. So I also want to observe a second thing, which is that for any connected graph G on gamma, the co-boundary map, so this, I'm not assuming equivariance of the graph, it's just a graph, so I'm not really doing dynamics here, I'm just doing cohomology. The co-boundary map for this graph still coincides with the homomorphism from k to the gamma to k to the gamma mod k, just because the graph is connected. Okay, so now the idea of the proof is the following. you pick a measurable graph G on k to the gamma mod k with connected components equal to the gamma orbits and with 1/2 the average degree of G less than the supremum cost of gamma plus epsilon. So you fix some epsilon beforehand. Okay? And now G gives you a measurable family of graphs. You know, on every orbit you have a graph. But in particular, it gives you a measurable family of co-boundary maps. And so in particular, you get, using this measurable family of co-boundary maps, just as we did here, you get a partition P, which just describes at every point the difference along the outgoing edges. You get a partition P, and the cardinality of P is bounded by the maximum degree you see in all of G times log k. All right, but now this is bad. This isn't quite what we want. So what's bad is first, the bound on P is bad. We don't want the maximum degree of G. We want the supremum cost. We want something like the average degree of G instead of the maximum. Well, of course, we'll be looking at Shannon entropy, not cardinality, but still. This is sort of a problem, understanding P. The second bad thing about this construction is that actually, it may seem surprising at first, but P is not generating. The partition P you get by applying this measurable family of co-boundary maps. P tells you for every point what the difference is along its outgoing edges in the values. It tells you the values, right, the actual differences. It doesn't tell you what the edges are. It doesn't tell you where the edges go in this measurable family of graphs. It's a little subtle, but P is actually not generating. And so to fix this, we do the following. So right at the beginning, you pick a partition beta with small Shannon entropy. You need a little bit more, actually. You need, when you look at the G invariant sigma algebra generated from beta, you want that to correspond to a factor where the action is still free. But that's maybe a minor detail. And now, so you pick the beta first, actually, and then afterwards you pick this graph G to be measurable with respect to the G invariant sigma algebra generated by beta. Then beta, together with this partition P, is generating. And the reason is that with beta, you can see where the edges go, because you can see the graph. And then with P, you can see what the differences are along the edges. Okay, so we have a generating partition. And so now we can say something about the rockland entropy. So a very useful property of rockland entropy is that it has a subadditive property. I won't say what that subadditive property is in general, unless you want me to, but in this particular situation, this subadditive property says that the rockland entropy is actually bounded by the Shannon entropy of beta plus the conditional Shannon entropy of P given the G invariant sigma gamma invariant sigma algebra generated by beta. And so the Shannon entropy of beta is at most epsilon. And now here, I didn't tell you what conditional Shannon entropy means. But it basically, what it is it says basically, given all the information about beta, and it translates, on average, what's the Shannon entropy of P in some sense? On average, how large is this partition P? And so now this helps us, because we're saying on average. I mean, I'm not giving you the definition, but basically the conditional Shannon entropy allows you to discuss averages relative to this sigma algebra. And once you work relative to that sigma algebra and you look at averages, then the degree of G, instead of getting the max degree, now you get the average degree. And yeah. And now I forgot to say, to get this half, you need to direct the edges so you don't count edges more than once. That's how you get the 1/2. But and so that's the basic idea of the proof. And so I'll stop here. Thank you for your attention.
Are there questions or comments?
Can you define, or can you calculate rather, the rockland entropy of a Markov-chain on a free group?
No. So there's a big problem with rockland entropy at the moment, which is there's no known method. So it's still very young. It was only defined a year or maybe 2 years ago. But at the moment, there's no known method to give a positive lower bound to rockland entropy without using sofic entropy. Sofic entropy is always a lower bound. And so it's a big open problem to find methods to give lower bounds to the rockland entropy. And this problem is significant. It would have significant consequences. I showed in one of my papers that if every group, if every countable group, every countably infinite group admits a free ergodic action with positive rockland entropy, then it follows that for any countable group, the rockland entropy of a Bernoulli shift is the Shannon entropy of the base, and that Gottschalk's surjectivity conjecture is true, Kaplansky's direct finiteness conjecture is true. So it's a big problem to find a way to show it's positive, yeah.
No questions? Should we find from